So it's our tradition to start 3 minutes past the hour. We call it lancing time. At least I do. Welcome, Efric. Welcome, Spartans. Welcome, guests. It's my pleasure to introduce our speaker today. It's Athanasios Psaltis. And Athanasios, it's really exciting to have you here. You are going to be the first in-person speaker in this serious Efric theory seminar. So welcome to Efric here. And so Athanasios did his PhD in 2020. At McMaster University, and then moved on to my alma mater, TU Darmstadt in Germany, working with Almudena Arconis on astrophysical uncertainties in core collapse supernovae and neutron star merger simulations. So Athanasios will tell us today about constraining nucleosynthesis using observations, simulations, and nuclear physics. Take it away.
Thanks. Okay, thank you, Christian, for the kind introduction. Hello, everyone. I feel a bit stressed now. It's the first meeting in person, so I have to deliver. So it's pretty interesting that it's the first theory seminar, but I see most of the people here are experimentalists, but that's fine. So today I'll be talking to you about a recent work that I'm doing in TU Darmstadt. You can find the preprint over here. And it's a new way of combining observations, nuclear physics and astrophysics to constrain nucleosynthesis in core collapse supernovae. So before I start, I would like to thank my collaborators for all their help, because it's a collaborative work. It's not only me that's working. And you might see some familiar faces. You might see your own face in this slide. So what I want to convey in this slide is that I like collaborating with people from different disciplines in nuclear astrophysics, with experimentalists, nuclear theorists, observers, and astrophysical, and people that are doing theoretical astrophysics. And in a sentence, what I would say, what Athanasios is doing in his research is that I'm studying how the nuclear physics and the astrophysics can explain the origin of the elements in the universe. So what we observe in the solar system, in stars, and in meteorites. And in general, my philosophy about nuclear astrophysics is that it's an undivided whole, so it contains information and techniques from many different aspects of science. And we can, let's say, we can simulate that with a jigsaw puzzle, where each puzzle piece contains different information. So for example, geology, we need to know stuff about geology because we're using pre-solar grains, these very small tiny specks that we find in meteorites, and contain information of balances. I'm pretty sure everyone is using statistics for their analysis and their work. Obviously, the people that are working with simulations, they have to use the latest algorithms that are coming from computer science. And of course, the triplet over here, nuclear physics, astrophysics, and nucleosynthesis. So nuclear physics, we want information both from experiments, experimental measurements, and also from theoretical nuclear physics. And astrophysics is pretty much the same. We're using simulations from different astrophysical environments, and also observations of stars and meteorites and so on. And these are connected by nucleosynthesis, which combines those two and tells us what's the production of elements in different astrophysical environments. So that's the plot, the figure that I will show you throughout this seminar. And first, we'll talk a bit about astrophysics. Okay, so this is a picture of a very well-known star for nuclear astrophysics. It's called HD 122563. It's the brightest star that you can find, the brightest metal poor star that you can find in the galaxy. And that's why, because it's almost 1,000 light years away from us, so it's not very far away. And this star has also a different name. It's called the Honda star, because lots of work has been done by Satoshi Honda, a Japanese astronomer, on this star. And these metal poor stars are actually extremely important for astrophysics, because astronomers can gather the light that these objects emit, they can analyze it, and they can tell us what this star is made of. And we're extremely interested about these old stars because they're probably polluted by a single or few nucleosynthesis events. So by constraining what happens in these stars, we can learn more about the origin of the elements. So something I forgot to mention is that this star is located in the Hertzmann constellation. It's a northern hemisphere, so you can find the constellation. I'm not sure if you can see the star. And now let's see what these stars can actually teach us. So here's a very simple graph. We have the abundance in a very weird way that astronomers are using. It's called log epsilon. And log epsilon essentially is a logarithmic of the number of abundance of a specific element divided by hydrogen, because hydrogen is very abundant, and then you subtract 12 versus the atomic number. And we're focusing only on heavier elements. You see with atomic numbers above 38. And in this figure, in this red line, you see the solar arc process pattern. And a word of caution is that when we're talking about the solar arc process, we're just talking about the total amount of abundances for these elements. And then we subtract the S process contribution, and then we also subtract the P process contribution. So it's a bit complicated, and we're not super confident that that's exactly what's the arc process abundance pattern. So there might be some changes either from the S process or from the P process or from another different nucleosynthesis process. So right from the bottom, we can see very nice features that come from nuclear physics. We see the zigzag effect. We see some peaks. So the second peak and the third process peak, which come from the closed neutron cells. And now if on top of that, we put observations from metal poor stars, like the one I showed you in the previous figure, we see that. So this is a very interesting result. First of all, we observe that here in the region of the rare element P, of the rare elements, we see a very nice agreement between the observation of metal poor stars and the solar system. And that tells us that there's a very nice robust arc process which can create those elements over here. And then if we see on the extremes, on the very heavy elements, on the actinides, and the first arc process peak over here, we see discrepancies. So I won't go into details about this first region over here. There's a lot of work being doing right now about this region, but my research is focusing on the first arc process peak, and more specifically in the elements between strontium and silver. So we see that there is a very large discrepancy between the solar system and the different metal poor stars. So what we're trying to understand is how many arc processes, quotes, arc processes contribute to these observations and the production of elements between strontium and silver that we observe in stars in the solar system, and also we might observe soon in meteorites. Okay. So the site that we're proposing that these elements are produced is nucleosynthesis in neutrino-driven winds. So the other groups are proposing other sites, but here in this seminar we'll focus on these neutrino-driven winds. And this is a picture of the Cassiopeia supernova remnant. And now we will go back to our puzzle figure, and now we will focus on the nucleosynthesis part. Okay, so here's, we'll give you a very brief introduction about how nucleosynthesis in neutrino-driven winds occurs. This is a very simplified scheme. So we have in the center the proto-neutron star, which is the newborn neutron star, the baby neutron star. And as we go from close to the proto-neutron star all the way outside, the temperature is falling down from very hot, around 10 gigakelvin, all the way down to very low temperatures. What's really important is that as the explosion happens and we have this neutrino-driven wind, we have lots of neutrinos that are processing the material after the explosion. So very close to the proton-neutron star, we have mostly dissociated protons and neutrons, so neutrons. And what's very important for our discussion is to figure out the relative abundances. So how many neutrons, how many protons we have. And there's a number or a quantity that we're using in nuclear astrophysics, which is called the YE. And essentially the YE is the number of protons divided by the total number of baryons, so protons and neutrons. And that means that if your Y is below 0.5, it means that we have a neutron-rich material. And if it's above 0.5, we have a proton-rich material. So as these ejecta are expanding and cooling down, they're forming alpha particles. And since the temperature is still so high, what essentially happens is that we have this nuclear statistical equilibrium. So all the reactions and their inverse are in equilibrium, and essentially you create these iron peak nuclei. However, things change very fast as we decrease, as the things expand and the temperature is falling down. And what happens is that some reactions are starting falling off the equilibrium, mainly the alpha gamma, and the PN reactions. And these reactions are actually moving the nucleosynthesis into heavier masses. And that's the main picture of the so-called weaker process, which occurs when the composition of the wind is mildly neutron-rich. So the Y is between 0.4 and 4.49. And essentially, after temperature falls to around 2 gigakelvin, the Coulomb barrier is very high, so the reactions cannot actually occur, and we have a freeze out of the reactions. Okay, so now let's see. That's what happens in the start. Let's see how we can sketch that in the nuclear chart. So this is the familiar nuclear chart, all of you. We have the neutron number versus the proton number, and the weaker process is relatively roughly happening over here in this red square. And now I will zoom into this region, and I would like to show you in more detail the reactions that occur in that region. Okay, so this is a sample calculation that I have performed. So again, we have neutron versus proton number. So the temperature is around 5 gigakelvin. The different squares correspond to the different isotopes in the network. The color code corresponds to the mass fraction of each isotope. And the arrows correspond to the nuclear reactions that occur at that specific time step. So you see that there are many diagonal reactions. All of those are the alpha N reactions. And as the temperature is falling down, you see that these alpha N reactions are actually moving the nucleosynthesis towards heavier masses. And when temperature is falling down, we have the beta decays moving our material back to stability. And again, we also note here the strontium, lithium, and zirconium elements. So something that is very important for our discussion, and when we will later talk about experiments, is that all this reaction flow doesn't happen very far off stability. So we are a few units away from stability, and that means that maybe nuclear reactions in this region can actually be measured relatively soon. Okay, so another way to show you why these alpha reactions are important is by using this quantity called the time scale of a specific reaction channel. And here we have the temperature falling from left to right versus this time scale. And we see different channels. So we have the N gamma, gamma N, PN and NP, and alpha and alpha, and also the beta decays. So you see that the first reaction channel that falls off the equilibrium. So if these lines are together, it means that we have equilibrium. For example, this N gamma, gamma N, they never fall off equilibrium. They're always in equilibrium. The first channel that falls off equilibrium is this alpha N and alpha pair. And that's the main reaction channel that leads the flow towards heavier elements. And then at later times, we also have this PN and NP channel that splits. Okay, so now the next question is to ask, study the impact of these alpha N reactions for the weaker process. So before we move on, are there any questions in the first part? More than the Zoom? No? Okay, there's lots more coming. So if you have questions now, that's a good time. So now we will move into the puzzle again, and we'll talk about nuclear physics, and more specifically about theory of nuclear reactions, so theoretical nuclear physics. So given that these alpine reactions involve unstable nuclei, we don't have experimental information yet about their cross-sections. So when we're modeling this weaker process, we need theoretical predictions for their cross-sections and reaction rates. Since we're talking about intermediate and heavier mass nuclei, a good way to model these reactions is by using the Hauser-Feshbach formalism of nuclear reactions. A very simplified way of writing such a reaction, for example, here for the cross-section, is by writing down as a product of two transmission coefficients divided by the total number of different transmission coefficient channels, or the alpha channel times the branching ratio of a specific channel. And for people that have worked with Hauser-Feshbach before, you know that the main ingredients for any calculation with the Hauser-Feshbach code includes three main components. The first one is the neutron level density, so how many levels you have per MeV unit, the optical model potential, so the interaction between the nuclei, and the gamma ray strength function. Okay, so how well do we know these reaction rates? So as I said, we're using all these models to predict their cross-sections and reaction rates. And I would like to show you here that this modeling is actually not so good. And for this reason, we need to measure reactions experimentally. So here I have done a very simple calculation. So I used the reaction code TALIS to calculate the reaction rate of a strontium 93 alpine reaction. So we have the temperature versus a comparison between these theoretical rates to the standard reactive rate. So reactive is the one that we usually use for nuclear astrophysics simulations. And here we have 9 different alpha optical potentials. So the calculations are identical, and the only thing we changed is the alpha optical potential. And you see that in the relevant temperature region, there are differences up to 2 orders of magnitude. And obviously that difference will carry on, this uncertainty will be propagated in the prediction of elemental abundances for the weaker process. So we need to constrain these reaction rates. That's the message. In the work that I will show you in the next few minutes, I used the ATOMP version 2 alpha nucleus potential. So this is a new potential as in the market relatively recently, a few years ago. So the ATOMP is based on the double folding approach. So it uses the ATOMP version 1 potential and the imaginary part of Gutensaxon star potential. And the very nice thing about this particular option is that when you compare its predictions with experimental data, it usually agrees very well to within a factor of 2. So for example, in this plot, I have the data from a recent paper of the molybdenum 100 alpine reaction. We see the different alpha optical potentials. And here we have the baseline ATOMP, which is the dashed line. And if you tweak the value by 20%, there's a very nice agreement between the experimental and the theoretical prediction. However, we have to be cautious because all these comparisons have been done with reactions that happen very close to stability. So when we move away from stability, we have to be a bit careful about how much we trust these predictions. And these results are published. So all the alpha induced rates for elements between iron and bismuth, they are tabulated. And in this publication over here, so anyone in the community, they can use these rates for doing their own projects and nucleosynthesis calculations. So we have alpha gamma, alpha p, and alpha n reaction rates using this ATOMP version 2 potential. So the next thing is to try and see what's the impact of these new rates to weaker process nucleosynthesis. And now we will go back to the jigsaw puzzle plot, and we will combine everything together. So I'll show you things about nucleosynthesis, astrophysics, and nuclear physics. So we'll combine everything together in this section. So first we have to find out which conditions are the ones that produce these lighter heavy elements in neutrino given means. And when we're modeling these conditions, we usually use three components. So the first one is the YE that we talked earlier. So the composition of the ejecta. Then we have the entropy and the expansion timescale. So how fast these ejecta are moving from the explosion. And here's the 3D plot with different conditions that we were calculated in the PhD project of Julia Bliss, who was a student of Arcones in Darmstadt. And Julia did a very nice job of creating parametric trajectories of different conditions that correspond and produce a weak R process. And also she performed a sensitivity study in which she used some of these conditions and checked the affine reaction rates by using the baseline calculation of affine reactions from Thales. And in our work, we used instead the atomic version 2 potential. So now let me tell you about the framework of the impact study I performed. So we start by selecting an astrophysical condition, so one of these dots over here, and then we have to sample all the affine reactions in the network. There are around 45,000 affine reactions, and for each of them, we assign a multiplication factor compared to the baseline of the atomic version 2, and we sample these reaction rates from an abnormal distribution, which has a mean of 0, and the size corresponds to a factor of 3 uncertainty to the rate. And then we perform the nucleosynthesis calculation using the WinNet code, and perform this loop for 10,000 times. So every time we resample all the reactions, we perform the calculation, resample, and so on for 10,000 times. And after we're done, we go back to the beginning, we select a new condition, and we perform the same flow chart again. Okay. So when you perform such a calculation for 10,000 times, you eventually get a distribution for each of the elemental abundances. So in this plot, we have for one condition the elemental abundance versus the atomic number, and each of these bands correspond to the 1 and 2 sigma uncertainties of the calculations. And what's really important is that all this uncertainty over here is coming only by changing the affine reaction rates. So everything else is the same, and every time I'm changing only the affine reaction rates. So these reactions are causing all these changes over there. So I think that which is new in this study is that we also performed, we said, okay, let's try and use elemental ratios instead of elemental abundances. And why elemental ratios? Because these ones are easily observed in metal poor stars. They're easier to constrain. And for this reason, we chose to do this exercise. So here we have a strontium over zirconium ratio, and you see a nice distribution. So that's a kernel density estimate for this ratio. And then we said, okay, we can do that for one set of ratios. Why not do it for 2? And if you do it for 2, you can get a 2-dimensional graph like this one. So here we have, again, on the x-axis, the strontium over zirconium ratio. And on the y-axis, we have the yttrium over zirconium ratio. And here you see the individual distributions. And this is the composite 2-dimensional distribution. And we have the 1 sigma and the 2 sigma distribution. So what's interesting is that on the bottom right here, you see this cross, which corresponds to the mean uncertainties you find in metal poor stars. And this uncertainty is pretty much close to the uncertainties we get only from the nuclear reactions. So we can constrain the nuclear reactions, so we can reduce the size of this distribution. We can pinpoint the conditions that can create these lighter heavy elements in neutrino-driven ejecta. Okay, so this is my favorite plot. This is the highlight of the whole study. I will walk you through. It's an empty plot right now, but we will fill it together. So now we have the strontium over zirconium rate versus the molybdenum over zirconium rate. And I have different pairs in the paper, so I will only show you this one here. And for the first time, we combine observations, astrophysical modeling, and nuclear physics uncertainties. So first, let's put the observations. So the stars over here, you might not see the stars anyways, the points with uncertainties correspond to metal poor stars that have this enhancement of first star process peak elements. And we think that these are the candidates for the weaker process. And the other stars, or the other points over here, correspond to other metal poor stars that we find in the galaxy. So now if we also include the baseline calculations for each of the astrophysical conditions we perform in this study, we get these colored points over here. And you see they're a bit scattered over the place. Some of them are they really disagree with the observations. Some of them are very close to the observations. But now, if we actually include the Monte Carlo aspect of the study and the nuclear physics uncertainties, these points become distributions. So now we have all these distributions from the different conditions. And this is actually I really like this plot because it shows us that some conditions are more sensitive to the impact of the alpha n reactions compared to other ones. For example, these ones over here, they create a very large blob, let's say, large distribution if you change the alpha n reaction rates. However, conditions like this one, they're more constrained. And that's actually something very, very interesting. So now let's see the next question to ask is which are the most important reactions? So if we can pinpoint which reactions can reduce the size of these distributions. And to do that, we actually perform a very simple test. So for each condition, we check all the reaction rates and we'll check the different elemental abundance ratios. We perform this Spearman arc coefficient. So essentially it tells us what's the linear relationship between two quantities. In that case, we're using the strontium over zirconium ratio and the variation factor of the krypton-88 alpha n. And here you see that if I put all these 10,000 calculations, I create this plot over here. And this plot tells me that when I increase the rate of the krypton-88 alpha n, I decrease the strontium over zirconium ratio. So essentially, I produce more zirconium than strontium. And since the correlation coefficient is minus 0.66, so there's a strong anti-correlation between the two, and that tells me that this reaction is important, and we need to study that experimentally. Again, if we perform this exercise for all the different conditions and all the reactions, we get to a final list of important reactions for the weak-R process. We have separated them into 4 groups or levels. The first group is the ones that affect many elements in many astrophysical conditions. So these are the most important of them all. Then we have the ones that affect few elements in many conditions, also important. And the next 2 are the ones that affect many elements in few conditions and few elements in few astrophysical conditions. So if you want to take a picture of those, you can do it now. Okay, so for the last part of the talk, we'll talk about experiments. So we identified these reactions, we did all these simulations, so now we have to go in the lab and study these reactions experimentally and figure out what's the effect that the new reactions will have to the production of in the weak-R process. Again, the last time I saw this slide for today. So we'll move again back to the nuclear physics part of the jigsaw puzzle. And again, we'll talk about experiments. So this is another plot from the paper that I really like. In this plot, I have put all these elements that I showed you in the previous list. And I have color-coded them according to the expected beam rates from the second pack of FRIF. So almost all of these reactions, all of these isotopes will have available beams at FRIF, and we can perform experiments with them very soon. And as I said again previously, we are talking about isotopes that are not very far from stability. They are very close to stability. And for this reason, they are relatively easier to perform. Before we move into the future experiments, let's talk a bit about what has been done so far, because study of alpha reactions is actually a very active field right now. There are many experiments going on, and I will talk about them right now. So first we have the AOMP group in Debrecen. So the AOMP group is using this activation technique. So essentially, they're using intense beams of alpha particles to beams on the target, and then they excite, they create these reactions, and then they get the excitement after many half-lives. And they have studied many of these alpha reactions. All of them, as you see, are stable nuclei, except Q26, which is very long-lived. And two of these measurements have actually been published in these papers last year. So here, of course, we have the local group, NCL, so Habanero and Sekar. They also have studied these experiments, and analysis is undergoing, and hopefully in the near future, we'll get some results from this group as well. Then we have the music group at Argonne. So at music, they're using an active target detector. We'll talk a bit more about that in the next few minutes. And they have published measurements of the molybdenum-100 alpha reaction earlier this year. And finally, in order of the board, we have Triumph. So at Triumph, they're trying also to perform measurements of alpha reactions using the EMA recoil spectrometer. And now I want you to look at this list and tell me if you see something familiar. Do you see something in these four groups that they're doing? No? So they are all studying the Q26 alpha N. Q26. So in the near future, we'll have 4 different data sets for the Q26 alpha N. So it will be the most well-studied alpha N reaction in history. Okay, maybe the carbon-13 alpha might be more. That's okay. Okay, so now let me talk to you about 2 experiments that we're planning. The first one is the strontium 93 alpha N reaction at music. So this is a proposal that I have put forward last year, and it was accepted by the local PAC. So a few things about music. Music is, as I said, an active target detector. Essentially, it's an ionization chamber with segmented anodes, and it's filled with gas. So in that case, it will be filled with helium gas. And what's really cool about these detectors is that they're both detectors and also targets. And as the beam is traveling through the target, it loses energy. And you can also study a large range of excitation energy just using a single energy for the beam. In that experiment, we'll use a strontium-93 beam from the Caribou fission source, which will be reaccelerated to the energies we want. And here are some sample calculations, so some simulations to show you that this experiment is feasible. So at music, they're using the energy loss between different strips of music. So if you take, for example, 3 strips over here and 5 strips over here, you can create this 2-dimensional plot. And the different blobs correspond to different reaction channels. So this is the alpha N, which is very clean. And then you have also the alpha P, the alpha alpha, and the unreacted B. And last week, or almost 10 days ago, the last experiment of NSCL happened. It was, guess what, the Q26 alpha N reaction with music. And these are some very preliminary results that we have. So these are events that happen in the 3rd strip of music. So it has 18 or so strips. So you can reconstruct the reaction and what's happening. And these black lines correspond to the unreacted beam. And the ones that are red, which have higher energy loss, correspond to the reaction products. So there we might also have some alpha-alpha scattering events, but with lots of analysis that will clean up and we'll get the final results for the cross section. So the final thing I would like to talk today is measurement of alpine reactions using SECAR here at EFRE. So SECAR is a recoil separator. It's a very powerful and versatile machine. So it was designed to study P gamma and alpha gamma reactions in inverse kinematics relevant for astrophysics. However, due to the fact that it has a very large acceptance, it can also be possible to study other reaction channels, such as alpha N, Pn, and so on. So to give you a brief description of how these SECAR experiments will work for alpha reactions, we have a radioactive beam from BF3, and then you have a GEMSA target, which is a jet target that shoots helium gas. Around the target, we can put the lambda neutrino array to detect the neutrons from the reaction. So the reactions are happening. Everything is forward focused. So you have both unreacted beam particles and reaction products, or recoils, as we call them. And SECAR is very good at separating those two. It has two velocity filters and a set of many detectors on the final focal plane, like an ionization chamber, a silicon detector, and also MCPs that can be used for time of flight measurements. So SECAR is right now under commissioning, and recently there was a measurement of this the K96 alpha N reaction, and hopefully soon we can put forward more proposals for SECAR. Okay, so what's the end goal? So again, I'm putting my favorite figure from the paper, and what we expect in the next few years is that by having more observations of metal poor stars and more measurements of these key alpha N reactions, we will change this figure from this one over here to that. So we'll have more observations, and by measuring these critical alpha N reactions, we will decrease the size of the distributions for many of the astrophysical conditions. Okay, so to sum up, I showed you that we used for the first time observations, astrophysical modeling, and also nuclear physics uncertainties from a new alpha optical potential to study weak arc process nucleosynthesis. In the near future, experiments using radioactive rare isotope beams will shed light on the production of these first arc process peak elements. And what I'm most excited about is that the framework that I showed you today can also be used for different kinds of nucleosynthesis. And you can only have to change the astrophysical conditions and the nuclear physics input. For example, we can perform a similar study for the main arc process and changing the N-gamma rates, or changing the pair decay rates, or the nuclear mass, and so on. So it's a very versatile tool and can be used for many different applications. So with that, I would like to thank you for your attention, and I look forward for the discussion.
Thank you, Athanasios, for the interesting talk. So questions? Yes, Chris.
This is really interesting interdisciplinary work. I had a question about the experimental part. So the temperatures are really high.
Yeah.
Several gigakelvin, and you measure the cross sections on the ground state. But there must be some thermal population of excited states and some other enhancement factors. So I'm wondering, if you imagine you can measure the cross sections perfectly in the lab, what would be the uncertainty left over associated with the stellar?
Yeah, that's a very good point. I think, okay, there are two things. The first one is that if we measure these reactions in the lab, we usually constrain them to within, let's say, worst case 50%. So that's still much less than the factor of 3 that we're using in this study. So again, everything will be decreased, and this uncertainty, this distribution will become smaller. The other thing is that in these energies, we might also have contribution, except for what you said, we can also have contribution from the 2N channel. So you have 2 neutron emission. And fortunately, in most of the cases, you don't have the 2N channel open in these energies. And mainly the 1N channel is moving the nucleosynthesis towards heavier masses. The other issue is that For example, at music, you're measuring the inclusive cross-section. So you measure all the different channels with this one energy. But if you're using, for example, Sekar and you're using Lambda, you can gate or see the 1n and the 2n events separately. So you can get the individual contributions to the cross-section.
Okay. Yeah.
You take your rate uncertainties at face value, then in your plot there were clearly observations that did not match any of the models. Is that the sampling of your trajectories or the model? So can you find trajectories that would reproduce the vibration, or is there a problem?
Yeah, no, actually there's no problem. So these ones, so the ones that we used for this study, they're actually a subsample of the ones that Bliss et al. Used for their study in 2020. But we can find conditions, or we can find a combination of conditions that can recreate the full abundance pattern for specific stars. So that was just a matter of, it's not the final work, it's just a way to see that what we did makes sense and it can be used for other things. So that's the first step of a long process in the future.
Yes, please go ahead.
Theoretical calculation of reactions in alpha in this area can have significant uncertainty related to the fact that probably all nuclei around D100 on both sides have significant probability of alpha clusters inside crystallization. And usually calculations don't take this into account.
Yeah, you're right, yeah. That's why you have to measure all of them. That's the argument from the experimentalist point of view. If you don't measure, you don't know.
So did that answer your question? Okay, fair enough. So you showed on several occasions your jigsaw puzzle.
Yeah.
So could you show it again, please?
Sure.
This is a deeper question than one might think. But what's your opinion on what's the missing piece between nuclear physics and statistics? I mean, given there's been a lot of progress in nuclear physics using Bayesian statistical methods.
Yeah. So I think, the paradigm is moving from the frequentist approach to more Bayesian. And that happened first in astrophysics mostly, but we see now also that it's taking over in nuclear physics as well. We see, for example, there is a paper by Caleb who performed WBA calculations using Bayesian analysis. And that's something that we'll see in the future much more often. And also maybe for nucleosynthesis calculations as well.
Right. So I think the missing piece in nuclear theory, at least, what concerns many-body calculations, ab initio many-body calculations, is the emulator technology.
Yeah.
So, I mean, for instance, eigenvector continuation that Dean Lee and his group and collaborators have made quite popular in nuclear physics, nuclear theory. So have you thought about using emulator technology in your calculations?
Not really, but I think it would be really exciting if you can use ab initio theoretical cross-section and rates for these studies. I think that would be probably the best to do.
Right.
Yeah.
So have you investigated this as well?
No,
okay.
no. But if you have anyone that I can talk to, please let me know.
After the seminar.
Yeah, okay.
So any further questions?
I think there's a raised hand in the chat.
Let me take care of this.
Yeah, sure.
Oh yeah, Pablo.
Okay, my connection may be poor. So my question is, where?
Sorry, Pablo, we can't hear you.
I think it's this.
Can you hear me? Oh.
Can you make it a little bit louder and just repeat the question?
Can you hear me?
Sorry, Pablo, just a second.
Yep. Okay, my
just
question
I
is,
think it's your laptop loudspeaker.
Yeah, that's my laptop. So my question is, where does this strong sensitivity to the optical potentials for the reaction rates comes from? That they can vary by an order of magnitude.
How the? So you're saying about the figure? Sorry, I'm going back and forth. This one, right?
Yep, here.
So what's the question again?
where does this strong sensitivity come from to the optical potentials?
Yeah, so essentially this has been.
Could you please repeat the question?
Yeah, so the question was where this. So the question is how this difference comes from the alpha potential. So there was work has been done in the past by Jorge and Fernando and Peter Moore, and they were trying to figure out which ingredient of the statistical model actually produces the largest uncertainty for these rates. And they found that the alpha optical potential is the one that is producing most of the change. But if Fernando wants to take on that or more, no. Okay. Yeah, I think
right,
that makes sense because you have an alpha-induced reaction. So it makes sense that in these masses, the alpha potential will be the most critical ingredient.
Right, but I would expect
Interaction
Coulomb
between
barrier
the
or
nucleus
something.
and the alpha particle.
Is it the radius of the potential sort of overcoming the Coulomb barrier, or what? What is the mechanism of this strong sensitivity?
What's the mechanism? So I'm
Behind
not
the
an
strong
expert on
sensitivity.
nuclear reaction theory, but I guess it's the interaction between the two. So if you're using a different potential for how those two interact, it makes sense that the cross-section will be different. Essentially, the probability of the reaction is happening.
All right, thanks.
Yeah, thanks.
Further questions in the audience or on Zoom? Pavel? You're okay. Great.
No, I'm done.
So you will like this question. It's about your favorite plot.
Yeah.
Can you show it again, please?
Sure.
So this is not my field of expertise, but I was just wondering. So yeah, exactly. So essentially, there's one true point or distribution function in this plot, right? And you have many
No,
different.
it's not one. So each of these ones is one different calculation.
Yeah, right. But I mean, the true result, whatever that is then somewhere in this plane.
So essentially,
my question is
Sure.
then, could you use some sort of Bayesian model mixing or so to infer, or some other
that's a
machine
future
learning?
word.
Okay, got it.
Yeah. So essentially, what Christian was saying is that you can create a distribution out of the observations, and then you can compare this distribution to what you get from the Monte Carlo.
And
But there could be some true scatter in
Oh.
nature as well. May not be unique true.
okay, so, why is that so? But my question was whether there's a point or an underlying distribution function. So I think that is covered in my question. But why is it not just a true result in this plane?
What do you mean a true result?
I mean, there has to be an exact. There has to be the value, the exact value that we are trying to infer with all of our tools, measurements, and observations.
Sure, but it's a bit more complicated when you have like different stars. They might have the same nucleosynthesis happening, but of course, a supernova explosion is a super complicated event. So there will be scattering within those events.
I see. So that's what you meant. Okay, got it. So you assume that. So it can be assumed that there's an underlying scattering of. Okay, so
No, we don't know. It could be either. It could be unique all the time, the same.
Right.
But there could be some true variation.
Okay.
Part of what needs to be figured out.
Okay. So in either case, it would be interesting to see how
Yeah, of course.
some sort of mixing. Probably mixing won't work well, but other ideas to infer the underlying distribution function.
Yep.
Okay, great. So any further questions? I don't think so. So let's thank Athanasios again. So our second seminar is going to be next week at the same time, same spot. And it's David Reinhardt talking about exactly about algebraic geometric classifications. So we are looking forward to that, and there will be cookies and coffee. So I'll see you there. Thank you.
Is there
Okay, I have code. So I guess I can upload it somewhere.
Yes, but
You also
let me
have it?
just, yeah, I think so. It should be on the computer.
Okay.
Some data, so
Yeah, the same.